Hello friends! In this video, let's continue our discussion of the 4 postulates of quantum mechanics. This is part 2 of the discussion. If you have not seen the previous video, I strongly encourage you to check it out first so that you'll be able to follow this video more easily. The link is in the description. As before, we will mainly be using the book on quantum computation and information by Nielsen and Chuang as a reference. The link to the book is in the description. In the last video, we have talked about quantum measurements but have mainly focused on just one type, which are the projective measurements. In this video, let's extend this to a more general formalism. First, recall that a projective measurement is defined by an orthonormal basis, which corresponds to the observable being measured. For a pure state psi, the probability of getting a particular measurement outcome I, associated with value AI, is given by the usual trace relation, which involves the relevant projector and the statistical operator of psi. Psi then makes the transition to the post-measurement state AI. This is similar to what we get by applying the projector I to psi, and we normalize this by dividing by the magnitude of this vector. We use the similar sign instead of an equal sign because the ket AI is only equal to the right-hand side up to a phase factor. The numerator of the right-hand side is this, while the denominator, since ket AI is normalized, this is just equal to. This is the magnitude of the complex number above, so dividing the two, we actually get a phase. This phase will simply cancels out for the statistical operator. The denominator for this is equal to the absolute square of the vector from applying the projector on psi. Note that although P is equal to P dagger by definition, we keep the dagger sign to prepare for the move beyond projective measurements. Once again, this term in the denominator can be written as a trace. Notice that the argument of the trace is just the operator in the numerator. This ensures that the trace of the entire term is equal to 1, as required of any statistical operator. We can rewrite the denominator using the cyclic property of the trace. Successive applications of a projector is simply equal to the projector. Thus, the denominator is in fact the probability of getting the measurement outcome. But do note that this is true only for projective measurements. We now have the description of the collapse of the statistical operator psi to an outcome state I due to a projective measurement. This is the projective measurement of a pure state, but it is a simple step to get to a mixed state, since each state in an ensemble is just a pure state. The probability of getting outcome I, given that the system is prepared in this state, is just using directly the result above. For the entire ensemble, just sum over all the probabilities. The probability of getting outcome I for the entire ensemble is obtained by the usual rule of classical probability, since we are dealing with a classical mixture after all. And ρ makes the transition to the statistical operator of outcome I after the measurement, which is proportional to. Again, this follows from the result for the pure state. Notice also that this operator in the red box is just a statistical operator of the mixed state. And we have the probability of getting outcome I given that the system is prepared in the mixed state rho. As we shall see, to normalize this post-measurement state, we once again divide it by this probability, just as in the case for the pure state. Once again, using the definition of the projector and the cyclic property of the trace, this probability can be written as. And we see that the argument of the trace is just the operator above. Therefore, we really have the right normalizing factor. The trace of the statistical operator after measurement is indeed equal to 1. Look at this transformation of rho. Recall that rho is a positive operator before measurement. This means its bracket with respect to any state must be greater or equal to 0. And after the measurement, the positivity of the state is preserved. We see this by taking the bracket of this transformed state with respect to an arbitrary state phi. This is positive as long as rho is positive. And this positivity is unchanged even if we include this normalization factor, which is just a positive number. Suppose if we replace the projectors P dagger by just any operator M and its summation conjugate. It is apparent that the positivity of the transformation would remain. This is obviously a much more general transformation, since Mi could be any operator, not just projectors. So let's use this to give a more general description of the post-measurement state that corresponds to outcome I, rho I. This makes sense, because whatever may happen to a system, including the process of measurement, it must still end up in some quantum state or a classical ensemble of them. And this could always be described by a statistical operator, which is positive. Once again, we set the normalization factor to be 1 over the probability of getting the outcome I when the system is prepared in the state rho. Thus, in order for the trace of rho I to be equal to 1, this probability must be equal to the trace of Mi rho Mi dagger. By the inequality above, this trace is also positive, which makes sense for our probability. Let's see this explicitly. The trace is just the sum of the diagonal elements of this operator in some arbitrary basis B. However, there is one constraint we must impose. The sum of the probabilities over all outcomes must be equal to 1. This in turn will put a constraint on the operators mi's. These operators have a name. They are known as measurement operators. There's a set of them, one for each possible measurement outcome. Let's see how the condition in the blue box constrains these operators. Using the definition from the probabilities, their sum is given by, where we can use the cyclic property of the trace. For this to be equal to 1 for any state rho, this sum of M dagger M must necessarily be equal to the identity operator. Thus, we have the constraint for the measurement operators as required so that the probabilities sum to 1. To make a distinction from projective measurements, let's change the index I to M. The state in the red box is associated with a particular measurement outcome. But what if after this observer measured the system, she passes it on to another observer who has no knowledge of the results of the previous measurements. How would this second observer describe the system, just from his own measurements of the system? A reasonable answer for rho prime would be to just average over all the outcome states by their associated probabilities. A very neat thing happens when you do that. This probability cancels with the one in the normalization factor of rho m, and gives the following result. Notice that once again, the measurement transformation is linear in rho. Rho prime is the state that describes the ensemble of measurement outcomes. Making measurements on a particular outcome state M of, say, an observable, the average value is just given by the usual trace formula. For the state rho prime, the average of A over the entire ensemble is just the average over all the results for each M. Using the linearity of the trace, we have thus we get back the same trace formula for the average value of an observable, but this time with respect to the ensemble rho prime. The state rho m comes from what is often referred to as a selective measurement, that is, a particular outcome is chosen, while rho prime comes from a non-selective measurement. Thus we now have a general formalism for describing measurements. Note that the collapse of the state of the system to one particular outcome is in general a non-linear transformation, as can be seen from the post-measurement state in the red box. And we can easily implement such transformations just by choosing an arbitrary set of measurement operators. Let's go into a little details about how we construct these operators. The main difficulty is that they are not completely arbitrary and must satisfy this normalization constraint. Let's begin with an arbitrary set of operators that are not yet normalized and may not satisfy the constraint. We will show that by introducing an extra operator and rescaling the ones that we have, this new set would satisfy the constraint. First, notice that the sum of the configuration m dagger m over the initial set of operators is a Hermitian operator, and so it can be expanded in terms of its eigenbases with real eigenvalues. And since this is a sum of positive operators, the sum itself is positive, and therefore all its eigenvalues lambdas are positive. Let's factor out the largest eigenvalue, lambda max, from this expression. Lambda hat is just a fraction of the eigenvalues over lambda max, and is thus less equal to 1 by definition. The expression in the red box can then be written as: we shall use this to define a new set of rescaled operators M, as expressed in the blue box. Now we are ready to impose the constraint. As we have said before, we do this by introducing an additional measurement operator, M0, such that M0 dagger M0 is defined by subtracting from the identity operator the sum of the corresponding terms of the rest of the measurement operators above. The resulting operator also has lambdas as its eigenstates, but with eigenvalues 1 minus lambda hats, which must be positive due to how lambda hats are defined. Thus M0 dagger M0 is a positive operator, as operators of this form should be. Since all these eigenvalues are positive, we may also take their square root, And because the basis is orthonormal, the square root of the operator itself can be found in a straightforward manner. So let's define both m0 dagger and m0 as the square root operator. Thus, we have just shown how to construct a set of measurement operators that satisfies the normalization constraint from an arbitrary set of operators. Having now developed a general formalism for measurement, which gives us both the post-measurement state and the probabilities for outcomes, let us now consider a different scenario. Suppose we are only interested in the probabilities of measurement outcomes, but not in the post-measurement states themselves. In this case, we will only need a way to generate a consistent set of probabilities given the statistical operator of the system. We can get a hint from this expression for probabilities. Using the cyclic property of the trace, we have. And this term is obviously a positive operator. Let's denote these operators as EM. They follow naturally from the measurement operators. On the other hand, we could have started with a set of positive operators directly. These would also give us a set of positive numbers, which could be interpreted as a set of probabilities using the trace formula above. Plugging in the expression for ρ, the positivity is apparent. The remaining condition for this trace to be a probability is for the sum of the operators E's to be equal to the identity operator. This will ensure that the probabilities sum to 1. Such a set of positive operators is what is known as a POVM, which stands for Positive Operator Value Measure. It provides us with a measure for probabilities. This is useful when we are only interested in measurement probability and statistics, but not in the state of the system after measurement. Let's go back to the questions from the beginning of the last video that any complete physical framework must answer. The first is how to describe the states of the system. Quantum mechanics answers this with the state postulate. The states of a system are vectors in a Hilbert space, or an ensemble of them, as described by a statistical operator. The observables of a system are represented by sets of basis vectors and can be put together in a compact way to give the associated operators. All these are basically saying the same thing. The state of a system is described by state vectors. The third question asks, what happens when we make a measurement on the system? Quantum mechanics answers this with the measurement postulate. This is what we have just discussed, our general formalism of measurement, which describes the transition of a system to a particular measurement outcome, and assigns a probability for this outcome. The key element is the set of measurement operators which satisfy the normalization condition. This collapse of the initial quantum state to a particular post-measurement state has three important features. First, this is a discontinuous change. Second, it is non-linear in the initial state ρ, as we have pointed out earlier. And third, it is fundamentally probabilistic. This is what really sets quantum mechanics apart from classical mechanics. We could not predict measurement outcomes with absolute certainty, but must settle with a set of probabilities. Notice that the discontinuous change of measurement is closely related to its probabilistic nature. Now we move on to the second question, which we have so far not addressed. How does a system change with time? More precisely, how does the state of the system change with time? Since time is a continuous parameter in quantum mechanics, it is reasonable to assume this change to be continuous. On top of this, we assume this continuous transformation to be both linear and deterministic. In classical mechanics, we have described how states change with time in a continuous and deterministic manner, governed by some differential equations. This whole machinery could be imported directly into quantum mechanics with the states now described by state vectors. This makes sense since quantum mechanics is supposed to reduce to classical mechanics by taking some classical limit. Historically, this is how the dynamical law in quantum mechanics is derived, by making connections with classical mechanics. But the strongest justification is still the validations by experiments. Thus, it is reasonable to assume that these two properties go together. If time evolution is deterministic, then there are strong reasons to believe that it must also be a linear transformation. This was again argued in that paper by Giesen from 1989, mentioned in the last video. These two features have to go together in order not to violate the principle of relativity. This is closely related to our discussion about the indistinguishability of the different ensembles that correspond to the same statistical operator in the last video, and how otherwise this would allow the transmission of faster-than-light signals. It is a fascinating topic that we shall reserve for another video. Here, let's just quote the result. Let's now discuss how quantum states evolve in time. A key feature about quantum states is that the superposition of any two states must give a third state. How does psi change with time? Let's assume that we are at some initial time t equals 0. After some time delta t, if this superposition is to be preserved, we must have. This implies that time evolution is linear. This is in fact the simplest way for states to evolve, because if we know how two states evolve in time, we will automatically know how any of their superpositions evolve. In physics, we always try the simplest things first, and if it agrees with experiments, just roll with it. And the experiments agree. Since we are assuming that the time evolution of quantum states is linear, this transformation can be implemented by a linear operator. Let's call it u of delta t. What properties must this operator have? An obvious constraint is that a quantum state must evolve into another quantum state, and quantum states must be normalized at all times. This is so that the probabilities of any measurement at any time sum to 1. Plugging in the transformation above into the inner product, we have For this equation to hold for any state psi 0, u dagger u must be equal to the identity operator. This is the same as saying that the inverse of u is u dagger. Any operator that satisfies this property is known as a unitary operator. Since any operator can be expressed as an exponential of another operator, let's express u as an exponential where the operator h remains to be defined. In general, h will also depend on delta t, because there is no reason for the exponent to be linear in delta t. But for simplicity's sake, let's assume h to be independent of delta t. We shall explain the general case in a minute. What are the properties of h in order that u is unitary? In order to evaluate the left-hand side of the equation in the red box, we would also need U dagger. Thus U dagger U is equal, which should be equal to the identity operator. Now multiply both sides of this equation by the inverse of U. This equation implies that H dagger must be equal to H. Therefore, H is a Hermitian operator, and so could be an observable of the system. In fact, this is known as the Hamiltonian of the system, and is actually the energy. The operator ut transforms the initial state into a state at time t, and is known as the time evolution operator. Let's calculate the time derivative of the state at time t. Using the expression for u above, we have H is assumed to be time independent. Since H also represents the energy of the system, this implies that we are dealing with an isolated system. And we end up with a first-order differential equation that describes the time evolution of the state vector. This is the famous Schrodinger's equation. Typically, this is written with the Hamiltonian of a particle moving in a potential. X and p are operators that represent the position and momentum of the particle. We have discussed these operators extensively in another video. Check out the link in the description if you are unfamiliar with them. Now that we know how a state vector evolves in time, we can apply this directly to the statistical operator. This extends directly to an ensemble. Thus, we have the statistical operator of the system at any time, given the initial state. Let's work out the time derivative for ρ. Notice that H commutes with U dagger. Let's switch their positions to get a neater result. Thus, the time derivative of ρt is proportional to its commutator with H. This first-order differential equation is known as the von Neumann equation, and is the operator counterpart of the Schrodinger's equation. The expression in the red box is the solution to this equation. Since this is a first-order equation, the entire solution should be fixed by the initial condition, which is ρ0 in the red box. Now we are ready to move on to the more general case, where H is dependent on time. This corresponds to the case where the system is not isolated, and its energy changes with time. Let's work this out for the Schrodinger's equation first. Let's not tackle this equation directly, but look at the unitary time evolution of a state vector for the general case. Here we are just examining an infinitesimal time evolution from time t to t plus delta t. Notice that this new unitary operator can also depend on the initial time. And we can proceed as before, putting u into an exponential form But this time, our treatment is more general. We need not make any assumption of a constant h. It is now just some operator that may be dependent on t. Furthermore, we keep delta t to only the first order, simply because it is infinitesimal. Again, let's calculate the time derivative of psi by expanding this to the first order in delta t. Bringing psi t from the right-hand side to the left, then dividing by delta t and letting it goes to 0, we have This is the more general case of the Schrodinger's equation with time-dependent h, as we have said. We can generate the solution to this equation by repeatedly applying the infinitesimal time evolution operator, starting with the initial state psi 0 to reach the state at any time t. This is the first step forward from t equals 0. Let's take another step. Continue this procedure until we reach the desired time. Which is some arbitrary n steps away. Note that the time in the argument of h in the unitary operators increases towards the left. If we consider h to be an ordinary number, then this expression can simply be combined into a single exponential as usual. This would be true if h at different times commute with each other, like ordinary numbers. But this is certainly not true for operators in general. So we have to modify this expression by a time ordering symbol, which is just a way of saying that this exponential must be understood in the sense of the green box, where operators at later times are arranged towards the left. We can recognize this sum in the exponent as an integral. Thus, we have a formal solution to the Schrodinger's equation with a time-dependent h. Usually, we can only evaluate this expression by using some kind of approximation, where some parameters can be assumed to be small, so that the exponential can be approximated by the first few terms of a power series. This is known as a perturbative expansion. We shall discuss more about this when a suitable application arises in the future. The important thing to note is that this product of unitary operators in the green box is itself another unitary operator. We can easily verify this by taking the Hermitian conjugate, then check using the definition of an unitary operator. Thus, even for a time-dependent h, the state vector evolves by an unitary transformation. This implies that a statistical operator transforms in the same way as before, but with a more complicated unitary operator. From the unitary transformation of the state and the Schrodinger's equation, the time derivative of this unitary operator is apparent. Checking our notes again, we notice that these two derivatives are exactly the same as what we have calculated for the case where h is time independent, except now h depends on time. This is not too surprising, since the Schrodinger's equation is in the same form as previously. With these two derivatives, we can once again calculate the time derivative of the statistical operator. Again, not surprisingly, we get an equation that preserves the same form as in the time-independent case. We have recovered the von Neumann equation for time-dependent age. Now we can answer the second question: how does a system change with time? Quantum mechanics answers this with the time evolution postulate, which are the results we have just developed. States undergo unitary time evolution. Often, we are just dealing with an isolated system with a time-independent Hamiltonian. In fact, if we expand the system far enough to include more parts, we will eventually end up with an isolated system. Which brings us to the question: how do we describe composite quantum systems? This should be part of the first question. Let's start with two systems. Suppose system 1 is in state psi1, while system 2 psi2. If the two systems could be described independently, then these two vectors are all we need to describe the composite system. This pair of states will be the state of the composite system. Formally, we denote this by a tensor product, but this is just a simple pairing of states. What about the transformations of states? The state of system 1 is transformed into another state by an operator A1 in the state space of 1, while for system 2, it's the same deal, but in the state space of its own. We can define this as the action of a composite operator, again with the tensor product. So each operator acts on the state in its own slot. Obviously, for the consecutive actions of operators, we have. What we have is just a direct extension of the formalism for single systems if we are describing them independently. The same thing applies for inner products. Cats contract with bras in their corresponding slots, and the result is just a product of inner products. We can justify this rule by an example. Suppose we would like to take the inner product of these two composite states, assuming that all the single system states are normalized. Notice that the state for system 2 for these two vectors are the same. The two composite states differ by just the state of system 1. State phi is just tagging along for the ride. Therefore, the inner product should just be the bracket of psi1 prime and psi1, which is also equal to, since the state phi is normalized. This is precisely our rule for the composite inner product. The next rule is less trivial, but is still a feature carried over from the single system. This is the superposition principle. The linear combination of any two product states must give another state vector of the composite system. Note that product states are just two single system states paired together by the tensor product, basically the kind of states that we are dealing with up till now. In general, we may not be able to express such a state in the form of a product state. This gives rise to interesting possibilities known as quantum entanglement. But that's a topic for another video. For now, let's complete the formalism for composite systems. Once again, we can look at a particular superposition such that the states for one of the system are the same and it's just going along for the ride. And the product states in the superposition differs just from the states of the second system. Therefore, it is quite reasonable for us to describe the state of system 1 as psi1 and the state of system 2 by the superposition in such a product. This argument shows that the tensor product is indeed like a regular product, and acts in a linear way. Next, we look at the cat-bra operator for a composite system. We just need to see how this acts on an arbitrary product state, and the general case will be apparent. This result is equivalent to. This means the cat-bra that we begin with is equivalent to this tensor product of cat-bras. All these rules define how the tensor product operates. This is how we combine the states and observables of single systems to form those for composite systems. In general, the composite states of two systems are just some linear combinations of product states. As mentioned earlier, these states are usually not product states. They are entangled. Entangled states are simply states that cannot be written as a product. We could of course have an ensemble of them described by a statistical operator, with the index alpha labeling the members of the ensemble. The way a composite system evolves in time is no different from a single system, which is a unitary transformation generated by the total Hamiltonian of the composite system. In general, H is a sum over pairs of operators that act on the states of each system. Omegas are the numerical coefficients. These include cases where the two systems interact with each other. The only constraint is that H must be Hermitian. The time evolution of the statistical operator follows directly from the result above. Everything we did for two systems can be extended in a straightforward manner to n systems. Again, we start with the product states, then form any superpositions we like. This is the composite state postulate, and provides the second half of the answer to our first question. And so we have the four postulates of quantum mechanics. These postulates are how quantum mechanics address the three questions that any complete physical framework has to answer. One might wonder whether we should make the distinction between a measurement process and time evolution. After all, a measurement is a physical process that takes place over time. Indeed, it is still an open question as to whether the measurement or the time evolution postulates could replace each other as the only postulate that governs quantum processes. This is the measurement problem in quantum mechanics. For now, we take the pragmatic approach that we always know whether a measurement has been made. After all, we are able to design apparatus that deliver definite measurement outcomes in a reliable and repeatable way. But nevertheless, we hope our viewers will be stimulated by this discussion to think about this question. In the next video, we shall introduce the theory of quantum operations, which is a general way to describe all quantum processes, including both measurement and time evolution. If you like this video, consider giving it a like and subscribe to this channel. And remember to press the notification bell so that you'll know when a new video is ready. See you next time, and thanks for watching.